In section 3.3, we're going to be looking at matrices. You may have been already familiar with matrices from maybe a matrix algebra course or a abstract algebra, or even maybe high school math. They may have introduced matrices. We're going to be looking at matrices and how to represent a linear map by a matrix. So first things first, we'll define what a matrix is. In this case, m and n are positive integers, so an m by n matrix is a rectangular array of elements with m rows and n columns. So m by n is rows by columns, right? So rows go like this and columns go like this, in case you don't know. Now the notation AJK, as you can see up here, denotes the entry in the jth row and the kth column of the matrix A. So for example, well, the first component, that would just be A1. Actually, I should have put equal. A1, 1, because it's in the first row and it's in the first column, so it's A1, 1. That's all that is. Let me just erase this. So an example, if A is our matrix, 8, 4, and then that whole component is 5 minus 3i, second row is 197, then A sub 2, 3 would be 7, right? Because it's in the second row. 1, 2, second row. 1, 2, third column, right? So that's why it's 2, 3. Okay, now suppose T is a set of all linear transformations from V to an element from all linear transformations from V to W, and V1 through Vn is a basis of V, and W1 to Wm is a basis of W. And the matrix of T with respect to these bases in the m by n matrix, MT, whose entries AJK are defined by, this is really important here. This is how we're defining our entries. So the transformation of vector K is equal to the linear combination of all those vectors in W. Now, most of the time we use standard bases for these. And actually, let me see what's next. So then, okay, so I should probably point out then. MT looks something like this, the matrix of the linear transformation T. It helps if we draw a matrix. And then at the top, I'm going to put just dot, 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 VK, dot, 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 W1, dot, 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 WM. So up here, we have basis, this is an I, basis of V. And over here, we have basis of W, right? So I lined up the basis vectors on the top to represent the basis of V, and each vector corresponds to a column, right? So V1 is a first column, Vk is the kth column, Vn is the last column, which is n. Similarly with the W's, these are the rows, first row, the mth row, and everything in between. Now here, so again, just keep this in mind. We're going to be using this a lot, that I'm circling again in red. We're going to keep that in mind. So right here it says that the kth column of MT consists of the scalars. This is important. The scalars needed to write TV as a linear combination of this basis, as our definition is telling us, such that we get this form. T vk is equal to the sum from 1 to m of ajk wj. Now that's a lot. What does that even mean? Well, first of all, this is just rewriting what we saw up here. But let's turn to the matrix. Let me show you a bit of what that means. So in this case, we're gonna here have the component A because it's matrix A, and then it's in the first row, kth column. So A sub 1k, and it's like that, dot, 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 all the way down to A sub row M, column k, right? So all those are just scalars, right? These here are scalars. Now the way this linear transformation goes is the linear transformation of vector k is you get, I'm going to change to a different color, you get all these scalars for your linear combination, so A sub 1 k, and then times the basis vector of w, which is w1, so w1 plus, and then you keep doing the same thing, A sub 2 for the second component, kth column. Now the basis vector of w, the second one, 2, so on and so forth, all the way to AM, our last row, kth column, W, WM, because that's our last basis vector of W. So that's how we're defining the entries of matrix A. And this again can just be rewritten as sum of from 1 to M of all the components of that respective column times the basis vector of W, or our image vector space. Or that was said poorly, but I hope you know what I mean. So that's what we mean. So I'm going to just go ahead and erase this. If you need to copy it down, go ahead and pause. Just because we have more information coming in. Okay. I'm just going to leave that circled in red because that is really important to keep in mind. Okay, so let's go over an example because examples help, right? So suppose T is a linear map from F2 to F3. And we define it by T of xy is equal to x plus 3y, 2x plus 5y, 7x plus 9y. We need to find the matrix of T with respect to the standard bases of F2 and F3. So first of all, standard bases of F2 and F3, F2 and F3, standard bases is 1, 0, 0, 1. Same thing for F3, we have 1, 0, 0, 0, 1, 0, and 0, 0, 1. Right? But the linear transformation, what is it doing? It's doing exactly this. It's telling us what it's doing. So if you want to try it on your own, go ahead and pause it. I'm going to show the solution of how we do this. Matrix T. Well, here, mapping the first basis vector, right? Just as we did up when I drew the matrix, right? I'm just going to draw it right here. V1, Vk, Vn. Right? This vector here is our first basis vector of V, or F2 in this case. So what does that map to? Well, we plug in 1 for x and 0 for y to this here, right? That's what our linear transformation is doing. So first component, 1 plus 0, because 3 times 0 is 0. So first component is 1, right? This is V1, this is V2, in which case v1 is equal to 1, 0, and v2 is equal to 0, 1. So second component of the first column, 1 times 2 is 2, plus 5 times 0, which is 0, so 2 plus 0 is 2. 7x plus 9y, we plug in 1 for x, 0 for y, we get 7. And the same thing for vector 2 now, that's right here, the second basis vector of f2. We get that the map or resulting components are 3, 5, and 9. Right, so here they explicitly told us what our what the linear transformation was doing, right? We just plug in those numbers. Now, up here it says if bases are not clear, then we just use this notation. We probably won't see this, not in a while, but just keep that in mind because here we're using the standard bases. It may not always be the standard bases. Okay, now we're going to move to a more familiar territory. And this is the sum of two matrices. So how do we add two matrices? Well, the sum of two matrices of the same size, that's key here, same size, is a matrix by we just add the corresponding entries. Right? So first column, first row, first column. We add those together, we get this. Right? Simple as that. That's why they have to be the same size. So we always have corresponding components for both matrices. Or in other words, this is simplified, but that's what we want. That's how we define sum of two matrices. A little good exercise for you is to prove this next theorem. It says suppose S and T are linear maps from V to W, then the matrix of S plus T is equal to the matrix of S plus the matrix of T. Okay, we have addition. Now we need what else? You probably guessed it, this product of a scalar and a matrix, right? So multiplying a matrix times a scalar. In this case, we're calling it lambda, the scalar. So lambda times a matrix, we just multiply every component, this component, all of them in between, or just basically all the components in the matrix by lambda, right? So lambda times our first component, first row, first column, all the way lambda times first row, last column, and everything in between. We just multiply everything by lambda, or as it says here, this is how we simplify what we just stated. Again, this shouldn't be too hard of a theorem to prove. Suppose lambda is an f, in other words, a scalar, and T is a linear map from V to W, then the matrix of lambda times T is equal to lambda times the matrix of T. Okay, so just a notation, because we do have a theorem using this notation coming up. This for m and n positive integers, the set of all matrices with that dimension, with those dimensions, m by n, m rows and columns, with entries in F, meaning scalar entries, is denoted by F, M, N, where they are M and N are superscripts now. So again, that's just the set of all matrices with that dimension. Well, here, a theorem says that this is a vector space. And, well, we already proved two important things of a vector space. Another thing is the additive identity for all matrices. Should come as no surprise, is a matrix with all zeros. That's additive identity. And actually the bases, or the basis I should say, of a vector space Fmn does it show it here? I don't think it does. No. Okay. So actually, all that theorem was telling us was, before I move on, dimension f n is equal to m times n. Oh, that's not times. Ignore that comma. N times n. Why is that the case? Well, if we have a matrix, right, m by n matrix, our bases, actually, okay, yeah. So our basis would just be 1 in the first component, 0 everywhere else, so on and so forth. And then, well, that's just one vector or one matrix of the basis. Another one would be, we take 0 in the first component, and then 1, and then 0 everywhere else, so on and so forth. And like that, we just put a 1 in one entry, or, in a matrix, have all zeros except for one entry. All zeros except one entry. Entry being 1. Right, that way, let me give you a concrete example. So that way, suppose, for example, the dimension of all 3 by 3 matrices, I keep messing up the notation, 3 by 3 is equal to 3 times 3, which is equal to 9. Why is that the case? Well, let's make this shorter, because the 3 by 3 matrices are going to take a while. Let's do 2 by 3. Is 2 times 3, which is 6. So all matrices with 2 rows and 3 columns of dimension 6, because their basis is 1, 0, 0, 0, 0, 0. This is a basis, right? So any 2 by 3 matrix we can get by some linear combination of those matrices, right? So for example, if you had 2, 3, 4, 0, 1, 2, we would have 2 times this one plus 3 times this one plus 4 times this one plus 0 times this one plus 1 times this one plus 2 times this one. And that is a linear combination that gives us this matrix. That's why this theorem holds true. That's our basis that we can always get that basis. So there's m rows and columns for possibilities of our matrices. Now let me erase this so I can present what's coming up next, which is pretty interesting. Something you have not known before, maybe. If you know if you know how to multiply 2 matrices, we're gonna see why mathematicians defined it like that. Let's see. Sorry, this is taking so long to erase. Okay. So now, how should we define matrix multiplication? Well, suppose V1 to Vn is a basis of V, W1 to Wm is a basis of W, and U1 to Up is a basis of U. Now consider the linear maps T mapping U to W, U to V, S mapping V to W, and the composition ST is a linear map from U to W. Does the matrix of ST equal the matrix of S times the matrix of T? Well, mathematicians wanted this to be a positive answer, right? Wanted this to be a yes. So what did they do? They made matrix multiplication. They defined it in a way that makes this true. So let's go ahead and go with the reasoning. Let's explain it. For 1 to P, we have that S times T UK is equal to this here. Now, why is it equal to this? Remember we had seen TVK, what that was equal to? I believe it was a sum of J equals 1 to M AJK W, this shouldn't be here, WJ. Remember that was the case? That's what we're doing here. T of UK is this exactly. If you need to verify that, go ahead. Just compare it to this on the left-hand side. It's the same thing, just changing some variables, the variable names. So that's equal to that, right? Now, this here are entries that are scalars, right? And we're adding all of them. So that's still a scalar. What does that mean? That means that we can bring it out and bring S in here times VR. So that's exactly what we did. S times VR, or this is the linear transformation. So it's going to take on VR, and this over here is just still scalar. So same thing using this reasoning. Now with VR, we get the following, right? So now this here is equal to this. That's what that was, right? And how? Using this definition, right? That's how we define the matrix of a V, the entries of the matrix. And then this over here remains the same. But now what can we do? We can rearrange things. We can put, bring this one outside, this sum. Why? Well, notice this. Notice how in our definition, TVK, this has to be on the outside. That's why we brought it on the outside. J from 1 to M, J from 1 to M. That's sum. WJ, WJ, that the vectors, the basis vectors. But now this AJK, how are we getting the components of that matrix? The way we're getting those components is like this. And what does this tell us? This tells us to add, I should point out here, these R and R agree, right? So what does that tell us? That tells us that we multiply from this matrix all the rows with their corresponding column components. Just as you knew matrix multiplication before, that's what this is telling us to do. And then you add them up. So for example, the matrix, what was the matrix? Let's go with 2, 2, 3, 1. 2, 1. And this is a 2 by 3. 3, 2, 1, 4, 2, 1, 5, 2, 1. This is a 3 by 3. Right, so here, this 3 and this 3 are the two R's, right? And how do you multiply those? Well, remember, this is going to be a 2 by 3 matrix. So it's going to be a 2 by 3 because we get the 2 from over here and the 3 from over here. And how did you get, for example, the first components? Well, you did first row times first column. That's why the R's agree here. So you did 2 times 3 plus 2 times 2 plus 2 times 3 times 1, which gives us 6 plus 4 plus 3, which is 13. So this would be 13 on our first component, given by exactly this over here that's telling us what to do. The sum of the this jth row times the kth column. That's why matrix multiplication is defined that way. Therefore, MST is an M by P matrix whose entry in row J and column K equals this here, which is exactly this over here. Right, so again, mathematicians defined it so that this would, we would get that the matrix of S times T is equal to the matrix of S times the matrix of T. And that was definitely clever. So now, suppose A is an M by N matrix, C is an N by P. Then we just get the rows, the entries. This is just basically telling us, hey, two matrices, A and C, we get them by what we just explained over here. That's how we get it. You multiply first row of the first matrix times the first column of the second matrix to get the first entry of our resulting matrix, and so on and so forth. Oh, well, it's telling us in words here. Right, so here's a multiplication. I know I shouldn't have done it now that we have an example, but it's a good example or another example to show how matrix multiplication works. So this first entry was by this first row times this column. 6 times 1 is 6, times plus 2 times 2, which is 4, so 6 plus 4 is 10. So on and so forth. And now we have the theorem. If T is a linear combination, a linear map, and S is a linear map as well from, T from U to V and S from V to W, then the matrix ST is equal to matrix of S times the matrix of T. And the proof for this is up here. If you notice, this is a light blue box because it is indeed a proof showing that this theorem holds. Okay, we move on to our last slide. This is just notation. So suppose A is an M by N matrix. If J is from 1 to M, then AJ dot, there's a little dot here. Just denotes the 1 by N matrix consisting of row J of A, right, of that matrix. So that's what that means. Just take that row. Similarly with over here, K, if there's a dot in the first spot, we just want to consider the kth column of A. So an example, if A is this matrix, then A 2 dot, we just consider what? The second row of A. which is exactly 197, as you can see here. Or if we have a dot 2, then we just consider the second column. So it's just 49. That's just the notation for that. So we have a theorem. Suppose A is an n by n matrix of C. Oh, sorry, and C is an n by p matrix. Then A times C, these here, these components are just equal to A times, or the jth row of A times the kth column of C. And you're like, wait a minute, well, isn't that obvious? That just comes from definitions? You're exactly right. This proof really just comes from definitions. Pretty much by definition, you're done with the proof. Same thing for this one. This proof is going to come directly from the definitions. A is an n by n matrix, C is an n by p matrix. Then the kth column of AC is equal to A times the kth column of C. And this one also, maybe examples would help you to see this. But it really is just a following by definitions. Now suppose A is an n by n matrix of C. Sorry, and C is this C1 to Cn matrix as an n by 1 matrix. Then A times C is equal to C1, that linear combination C1 times the first column of AC is a linear combination of the columns of A with the scalars that multiply the columns coming from C. And we're going to show an example, but it's nothing new if you have taken that matrix algebra course. So for example, this example here shows us that this matrix multiplied times this 2 by 1 matrix, n by 1, gives us exactly this, 7, 9, 1931. So more scalar multiplication. And this other one here, this here, we can take and make a linear, we can make it a linear combination by 5 times 135 plus 1 times 246. So compare both of these. They're basically actually the same. This theorem here is that example showing that example, how that works. And then compare these this example to the matrix where we were multiplying, right? Multiplying two matrices in the last slide. That's where I got these numbers from as well. So just make sure to compare these examples and see what theorem they correspond to.